Okay, so hello everyone. In today's class, we will be looking at vector and raster overlay operators. Okay, so first of all, we need to understand what overlay actually means. So overlay, it is a GIS operation that superimposes multiple data sets representing different themes together for the purpose of identifying relationships between them. So it's basically we would have different data sets in different files, in different vector files or different raster files, and then we kind of superimpose them, and we eventually derive a relationship between them, and that is called overlaying. Okay, so there are different overlay operations, and in vector and in raster, we do it differently since they are different data types. Exactly. Okay, so overlay operations, what we can see, talk about overlay operations is that it combines spatial and attribute data from two or more layers to create a new output layer. So the same thing, in this case, it describes the essence of it. And in this sentence, you can see what it actually is doing. So it combines the spatial and attribute data that is carried by that layer, by that shapefile or by that TIFF file or anything like that. And then it creates a new output layer overall. So there are some things that needs to be clear before doing overlay operations, for overlay operations to function, and that is the input data that we have, they should have the same coordinates. For example, if I'm working in EPSG 4326, which is WGS 84, so both of those shapefiles, vector shapefiles, they need to be in the same coordinates, and then only we can apply the overlay function, overlay operator in it, and then create a new file, and that would also be in that same coordinate system. So that needs to be there first, and then for raster data, what it should be is the cell should match. So what does it mean that it should match? That means it should match in resolution and orientation. The orientation of the cells, of the pixels, and the resolution should be same for those two or multiple raster input sets. So that needs to be there for overlay operations. So basically you can see here, so there's a layer A, and then there's a layer B. So you can see that layer A is somewhat of a polygons consisting of a cities or countries or anything like that, and layer B, it might be some kind of road network or something like that, right? And then we overlay, we'll see both of these layers together, and then that is a different layer. So for understanding the overlay operators, we have divided the section into two parts. So first we'll understand vector overlay and their operators, and then we will look at raster overlay and their operators. So when we are looking at vector overlay, in the vector domain, the overlaying of data layers is computationally more demanding than in the raster domain. And why is that so? We'll look right now. For here, you can see there's a layer 1 that consists geographic data, and the layers, and there are two different attributes, so 1 and 2. So class 0, class 100, so it's just a representation, okay? So we have a different layer in which 1 and 2 are different, and it's a completely different polygon. Exactly, okay, completely different polygon, but they lie almost in the same zone, but the division is different. So when we overlay both of these, what happens is it needs to retain both the features. So what happens is 1 2 1 2. If you look, this goes past here, and then now we have 4 attributes, okay? And then when you see, here's 1 0, 200, 110, 25. If you look here, then there's the combination of both of them, okay? So this is somewhat of what vector overlay does. Now you might wonder, can we only just overlay just two polygons? Because in vector we have found out that vectors are different types, right? So it can be point, it can be lines, it can be polygons, etc. But no. So when features of different types, like for example points, lines, polygons, are overlaid, then what happens is then the output will be of the lower dimension, and we can look at here. Okay, so the point is of here of 0 dimension, right? So if you look here, it doesn't have a dimension. And when a polygon layer is there, then what happens to the output layer is the output layer will always be formed of the lower dimension. So it'll be 1A, 2A, 3B. 2 is not there because 2 does not come under any A or B. So that's why 2 is question mark, and then 1A, 3B. You could look at this example. And if there's a line and if there's a polygon, So if this line passes through this section, what you can see is 10, 10's certain portion lies at this R, 10 certain portion lies at this S, so that's why 10R, 10S, and 11R, 11S, 12S, 12 question mark, because this part of the line, it does not come under any polygon. So you can look at this example and you can find out that since line is one dimensional and polygon is multi-dimensional, here maybe two, so what you can see here is the output layer is the line. So why is that so? We'll be looking at the other example as well, and then you will be clear why it is in that way. And if there are two polygons, what you can see is the part that is overlaid in both of them, 100, this section maybe, so there's 100R and 100S, and this part of the section, which is does not lie in either R or either S, it is 10, 100, question mark, 200, question mark. So question mark means null value, okay? So this is how the vector overlay function basically works. So now I'll show you in this example why it takes the output layer is always of the lower dimension. So you can see in this that the input polygon layer is a polygon, and this the input is a point layer. So right. So when this happens, what if the output layer is a polygon? So if the output layer is a polygon, we have X, ID is something, okay, and then we have county, and the name is green, and the class. So what will be the class there? Will it be HIC or UR2 or YO? So there's no clarity in it, right? But if you look at this, the output point layer, if the output point layer is a point, then you can clearly see that there's X type what? Since it's a county, okay, so name is green, green, green. And what is the class? Then you can look, the X is of A, so that's SIC, UR2, YO. So that's why the output layer is always of the lower dimension. So that's why when we merge these, when we overlay, we do not have an output polygon layer, we instead have an output point layer. So this example clearly explains us why this happens, okay? So this is the first thing you need to understand. Okay, so after understanding what vector overlay is, what is the basic understanding behind it, now we can move to the overlay operators, which is the main topic that we need to address today. So the vector overlay operators basically are of 4 or 5 different types. There are many of them, but yet the major ones are 4 or 5 of them, which we'll be seeing right now. So the first one is clipping. So what is clipping then? So for example, you have an input feature that has different classifications here in a square box, and if you have another polygon which is circle, when you clip, what happens is input is clipped by this feature, so that's why we get the output, this one. Okay, so you can see in this example as well. For example, in this square box, what you can see is it is divided into A and B, like rows, right? A and B. And if you look, we have a clipping feature of a circle, and that is overall 1. So what happens when we clip then? So clipping means it clips only the input feature with the help of the clipping feature. So in this, the clipping feature is the circle, and what it is clipping is this square. So we have only this output. Does it make sense? Okay, now it makes sense, right? So we only have this output. So what are the attributes that are gonna be in this one then? The attributes that are gonna be in this one is A and B, A and B. So we can see this with a different example as well, okay? So if you look here, we have catchments. So catchments are basically watersheds. So basically it is it is the cover area of basically a watershed of a watershed. So this is the Mississippi River St. Cloud watershed. This is the Rum River watershed. So each river has its watershed. So you might have seen studies where you have seen Marshangdi watershed or Bagmati rivershed, Bagmati watershed, Bagmati catchment. So that basically means the area that contributes to the water in the Bagmati river or in the Marshangdi river. In this case, this whole area's water contributes to the Mississippi River. So this is the Mississippi River catchment, okay? So this is catchment, and these are counties. So what happens is, when we are clipping the catchments by the counties, we will have features of the catchments, okay? So the counties acts as a border which clips the data of the catchments. So that is what I had shown here. Like we have features in the square, and the circle is just a clipping feature which clips the features of the square, and eventually the data we will have in our attribute table is A and B. Okay, does that make sense? Okay, so now we can see this example in QGIS as well. So let me make a shapefile. Okay, so I'll just create a shapefiles. Okay, so I'll create a folder where I can say it's about 4.3. Okay, makes sense. If you think the video is going too slow, you can just fasten the video speed. Okay, guys. So let me say it's a square, though I'll not be making a good square. Okay, square, and then it'll be a polygon. So since we need the same coordinates, I'll be working in WGS 84. Okay, so we will have this, and then what will I have? Its name. I'll keep its integer ID. Just ID? No, I'll keep an extra field as well. A new field. Its field will be haha. So add to fields list. It'll be a string of 80 words. Okay, this works for me. So now I'll create a polygon. Okay. No, wait. Let me work in this one. So toggle editing. I'll create a polygon, which will not be a perfect square, but let us suppose this is a square. Okay, for now. Enter. Right click. So the ID is 1. Haha, just name it haha again. Make sense? Okay. So I will save the changes in it for now. I'll create a different polygon now. Okay. So I'll create a polygon in the same file. Whose name will be circle. Okay, for now it's good. It'll be also a polygon, and then I'll create a different name list, which will be LOL. Add to fields list. Okay, makes sense. Okay, in this circle I will toggle edit, so I can edit now. I'll create a circle which will not be perfectly shit. So it's not a circle though. Oh shit. One, and then login. Okay, so now I have two polygons. Okay, okay. So I'll show you how we can do clip. So this is just a basic example. You can do it with the other spatial analysis when you're doing other complicated analysis, but this is just an example. Okay, guys. So now I'll first do vector, and in the geoprocessing tools I'll have clip. So they'll ask me what should I keep the input layer. So if I keep the circle, the square will act as the clipping overlay layer, and this will be input. Circle will be the input, and the attributes of the circle will be retained. Whereas if I say I want to do something else, then something else happens. So okay, for now what I'll say is it'll be square. The input layer will be square, the overlaying layer will be a circle. Okay, so it'll create a temporary layer, run. Okay, so now it has created a layer. If I close this, so it has created circle. Now if you remember, in the circle the attribute table was low login, right? So now if you look at the clip version, what do you think will be the attribute of this clip? Will it be the attribute of the circle, or will it be the attribute of the square, or will it combine both the attributes of circle and square? So as I mentioned before, when you are clipping, and since in our case right now the main input layer is the square, after clipping the square with the circle, it will retain the attribute table of the input layer. So for in our case, since square was our input layer, it will retain the attribute of the square. In the square, the attributes were haha, right? So if you look at the attribute now, so attribute was haha. ID and haha, so it'll retain those features. Okay, so if I close this one and if I look at its attribute table, it's ID and haha, right? So that you need to understand in clipping. Okay, so since showing you the again example for here, our input layer was a square with two rows, right? So A and B. In our case, there was just one when I showed you it in QGIS, but here it's two. And when we clipped it with this one circle, then it retained the rows of the square, which was the input layer, so A and B. Okay, so the same thing. So what happens when we do the difference then? So when you're doing the difference, what happens is it selects all those that is not overlaid by the circle. So it is the complement of clip. The difference is the complement of clip. So you need to understand that. So before, clip used to clip just this feature. Now difference would mean all those area which does not lie in this zone. So in this as well, it will retain the features of the input layer, which is a square right now. So A and B, A and B. Okay. So if you see the example here, I have counties, which is the input layer, and if I have a catchment, which is the clipping layer. So what happens when I keep this, when I overlay it here? So when I do difference, what happens is it selects all those layers. It keeps only those layers which is not within this clipping layer. So that is how difference works. So now let's look what intersection is. Okay, so we are discussing about vector overlaying operators. Okay, so intersection is a second one. The first one was clipping and difference. The second one is intersection. So what does intersection do is it keeps only those layers which are in both of them. And if you see here, what it does is intersect. So this is the same as you might say it is same as clipping, but it is not. Here it combines the attributes of both of those layers. So if you look here, there's the square, and then there's the layer of circle, and when it intersects, so there's A and B and there's 1, it keeps the attributes of both of it. So not just A and B. If it just kept AB, it was clipping. But now it is keeping A, A1, B1, A1, B1, A1, B1. So does it make sense? So yeah, if you look here now, this is the catchment. These are the counties. If you look, when you keep it overlaid here, you could see that counties come here in the catchments. So when you do intersection, it will create this layer. And now initially when we were just clipping, this green was just Snoke River, right? But no, the Rum River. But now it is Anoka County as well as the Rum River. So it will, in this attribute table, it will have features of both of them. So let's look with the example here. So this, I'll just rename it for our ease. So I'll clip, okay? Okay, so now what I want to do is, so now to remember you guys again, we have the attribute of lol in circle, and in square we have the attribute of haha. Okay, so that is the attributes. Okay, so now what we can do is we can do intersection. Okay, so the input layer, it does not matter whether the input layer is this or the output overlay layer is this. In this intersection you can keep any of them. So for me it's square right now, it's circle. Okay, so if I do run, close, I will have intersection. So now if you look at the attribute table, it will have ID haha, which is of the square, I assume, and ID and lol, which is of the circle. So it will combine the attributes of both of these. Okay, so but the product, it might look similar as clip, right? But if you look at the attribute table, it's completely different. So you need to understand this difference between clip and intersection. Otherwise, just looking at this, you might say that they both are the same, because if I close intersection, it's the same, right? But it's in the attribute table that it is doing the difference. Okay, so since you have understood intersection as well, let's go to union now. So when you look at union, what happens is there's the input coverage, there's the union coverage, and when you combine them, then it'll have features of both of them. So they wouldn't be clipping or they wouldn't be intersecting, but it'll be combining both of them. And how will the attribute table look like? It is shown here. So we have this square, we have this green. Now if you look here, there's AB and there's 1. So 1 meaning this part covered by the circle. So if you look here, when we are doing union, what you can see is this part. This part does not have any part of the circle. So that is just A and null value. This part has A as well and 1 as well. So A and 1. 1 meaning part of the circle. And then B as well. B nothing here. And B there is again 1. And here in this case, if you follow the cursor, there is no square but there is circle, so 1. Right? Does that make sense? Okay, so now if you look in the same example of catchments and counties, what you can see is there's a catchment, there are counties. When you keep it overlaid on, you can see where it lies. And what happens is when you yield the values, the part which does not have these counties also will have some values, but those values will just be the values of the catchments. And these values, where it has both the counties and the catchments, it will have Hennepin County representing the county and Mississippi River representing the catchment, right? So I think it makes sense, right? So now let's look how it looks in QGIS then. So here I have circle and square. I'll just do this both, circle and square. Okay, I'll bring it here. Okay, so let's go to vector now. Let's go to union. So input layer is our square and overlay layer is circle. So if you do run, close, what happens if you look at the attribute table, then it will have, so as I'd shown you earlier, okay, so let's open it here. So you can clearly see here we have 3 distinct regions here. So this is just part of the square and it does not have circle's component. So that's why if you look here in this one, in this one, its ID is 1. Okay, it makes sense. Haha is haha again, so it has value because it is a square. It has null value in both of these because this part does not have any part of the circle. Whereas if you look at this one, then this one has haha again as well and lol again as well, both these columns, because this part has the attribute of circle as well as the square. And again in this part you can see it has only the attribute of the circle. So this is how union works. Okay, so these 4 which I showed you are the main vector overlay operators that you will use in GIS. So there are some problems with vector overlay which you can see here. So there is the formation of slivers. For example, you have 2 polygons and their borders do not match or something like that. What happens is, what you can see here is, you can see these areas. These are just small polygons that will be formed. Those small polygons are formed because they do not come under any area, right? So they do not come under these overlaid area, and that problem will be there in vector overlay operators because not all the files are made by the same person, or even if it's made by the same person, there won't be a uniformity. For example, a Nepal's border made by someone and a Nepal border made by a different person will be different, right? And if we try to bring them both together, there will be the formation of slivers. So that is the major problem in vector overlaying operators. So let's look how we can use it as well. So how we can use vector raster overlay operators and how it can be used in real life examples. So for example, we have a wind speed map, right? So we have a census map as well. So if we need to find suitable areas where the wind is high, probably greater than 4 meters per second, and if we need a place where the population density is very, very low, 10 per kilometer square, so that area is considered to be good for wind farming. So we have 2 maps, and when we overlay, so first we need to reclass. We need to reclass because we have 1, 2, 3, 4, 5 to 7. So we need to first reclass into wind area where wind is less than 4, or area where wind is greater than equals to 4. and again we need to reclass this population density as well, where the population density is less than 10 per kilometer square and the population density is greater than or is equals to 10 per kilometer square. After we reclassify it and once we overlay each of them, then we will get a good map where the suitability of places where wind farming is feasible will be shown. So this is just one real life example in which we can use the overlay function. Okay, so this is just an example, so no need to be serious about it. Okay, so now looking at, after completing vector overlay operators, now we will go to raster overlay operators. Okay, so what you need to understand first is raster contains cells, right? So for raster overlay, it's comparatively easier than vector overlay, because in vector overlay there will be we'll be dealing with geometries, we'll be dealing with shapes, polygons, points, lines, so it'll be complicated. But in raster overlay is possible only when the cells are uniform, so it should have same resolution and it should have the same orientation, right? So once that is done, once that is there, then the raster overlay is comparatively easier than the vector overlay. And if you see, the cell values are concatenated, which results in new values in corresponding attribute table. So what happens is, for example, we have a layer A that has AA, BBB, A meaning loamy soil, B means clay soil, okay? And we have a geographic data. So 2, 3, so all these representing forest, urban, farm. So what happens when we overlay? So what happens is it concatenates. So it combines both the features. So we have A2, B3, B3. So we can see, and the attribute data will combine as well. So this is one basic how the raster overlay functions. So now what you can see here is, so let's look at this example. For example, what intersect means in raster is, so we have a road where 111 represents a road and 0 represents all those areas which does not represent a road. And we have a different TIFF file, which is raster file, that shows land cover, where 5, 4, 2, 3, 1 means different thing, where you can see that blue means maybe river, and green means maybe forest areas, yellow means maybe barren areas and all. So if we intersect both of these, so what I need to know is, what you can see is it just multiplies here. So here, so 1 into 5, 1 into 4, 1 into 1. So if you look here, it is representing, what you can see here is wherever it is representing 0, it is the place where there isn't a road. And where there are values, you can see that it is road as well. And then the values, the attributes of the land cover is also retained. So this is one example of intersection in raster, sorry. And if you look here, so add and score, what you can see here is there isn't just a null value, or there isn't just 0 and 1, but instead we are adding and then we are ranking it. So if you look here, there are 3 different raster files. We are adding it. So where there are all zeros, these are null values, and where there are no 0 values, we can not just see binary values 1 and 0, we can see 1, 2, 3. So we are just adding it. So it might be used for ranking. So vector overlay operators are useful, but geometrically it's complicated, and this sometimes results in poor operator performance. Raster overlays do not suffer from this disadvantage, as most of them perform their computations cell by cell. So most of the computations are done cell by cell. So that's why it prevents the errors of slivers that usually occurs in vector overlay operations and other geometrical complications as well. So some of the raster overlay operators which we will be discussing are arithmetic operators. So multiplication, division, subtraction, addition. So mode, which means 10 mod 3 resulting 1. So it is the remainder. Division 10 divided by 3 is the quotient. So it's the 3. So in this, these are some of the arithmetic operators or the mathematical operators. So here, if you look, these are the values of the raster cells, and if you add 10 to all of them, so it becomes this. Similarly, if you add a plus b, what happens is this happens, right? And what happens when you do this operation then? So it'll form some value, and this operation is commonly known as NDVI in remote sensing, which is normalized difference vegetation index. And this NDVI is a good indicator of the presence of green vegetation. So it is usually used to see the presence of chlorophyll. Okay, so this is one term which is represented by this operation. Okay, so this is arithmetic operators, how it can be used. Whereas if you look at comparison and logical operators, what you can see is in the comparison operators, if you look at this operator, you can easily say that this is a comparison operator. Okay, so you'll store truth values, either true or false. A cell value in C will be true if the cell's value in A differs from that cell's value in B. It'll be false if they are the same. So this is used. So these are some of the comparison operators. And if you look at the logical operators, these are AND, OR, XOR, and NOT. So AND means, as you know, for example, if you look at A and if you look at B, and if green means, for example, here true or maybe 1, and this all these values in white, it represents 0 or false. So AND means if it is in both A and B, then it is AND, right? So A and B. So in these cells, it is true in both A and B. And if you look at A or B, I think like you just need to have true or value 1 in either A or in either B, then it functions this way. And A XOR B, I think you need to understand this one. And what A XOR B means is, like if you look at these data sets, you can see the layers where neither A or neither B lies, right? So if you look clearly A XOR B, so what happens is, if you look at these 3 by 3 cell here, and if this by 3 by 3 cells, this green one, it does not have A, and it has A, but it does not have B, right? So that's why this one is there. And similarly, if you look at this cell, it has B, but it does not have A. So this cell as well. So A XOR B means those cells which have only A, or those cells which have only B. So these cells are A XOR B. And then we have a NOT function, NOT logical operator as well, which is A and not B. And we have, if we can do in this way also, A and B. First we'll do A and B, and then after getting A and B, this one, we'll again compare this with C, okay, or C. So in this way, there are different logical operators as well. So comparison and logical operators are another type of raster overlay operators. So if you look here as well, what you can see is A is equals to forest and B is less than 500. So we need such values where A is forest as well and B is less than 500. So this D1 is the layer. Similarly, D2, A is forest or B is less than 500. So the same thing, but here we are just representing without values. Here you can see values as well. So the same thing, if you look closely, you'll easily find the distinguishing. So in this way, the raster like overlay operators work. And this is possible only because A and B, they both have the same cell. That means they have the same resolution as well as they have the same orientation. If both of these were not there, then we couldn't have been able to perform raster overlay operators. So you need to understand this before performing any raster overlay operators. And there are conditional expressions as well. So in, for example, if we are using conditional expressions, so this is how the syntax would probably look like. So if there's a if, and you have a condition, and then if this is fulfilled, then this expression will be there. And if this condition will be false, then this expression will be fulfilled. So if you look here, we have forest and null values, right? So if A is equals to forest, true, otherwise null value. So that means wherever there is forest, there is true, and wherever there is no forest, there is null value. Similar case, if A is forest and B is equals to 700. So which are the cases is, if you look at these up 7, this one, and if you look here, I think this much satisfies it, right? So if you look here, this should also be satisfied and this should also be satisfied, and then those cells will be true, other all will be false. Okay. So we can further do complicated analysis in this with the aid of decision table and conditional operators. So we have a land use raster here and we have a geology raster here, okay? So this alluvial and shale are the geological properties and this land use properties. So if you look here, what you can see is now we need to look at this. We need to do intersection or something like that. We need to overlay them and we need to identify which are suitable, which are unsuitable areas, okay? So if you look here, for example, and they have given conditions as well. If there is grass and if there is alluvial soil, that is unsuitable. If there is grass and there is shale, that is suitable. If there is lake and there is alluvial, it's unsuitable. In both cases of lake, whether it's alluvial or shale, then it's unsuitable, right? Because we cannot do anything there in the lake. So we have a land use raster here, we have a geology raster here, and this shows us combination. So here, if you look here, so this much is red. Why? Because this is, if you look, it is a forest area, right? It's a forest area, and if you look here, this is the portion of shale. So forest and shale is unsuitable, so unsuitable. So in this way, they have created this is a table as well, combined with this conditional conditional operator. We can easily find which site is suitable and which site is unsuitable. So for that, the syntax probably would look like if land use is forest and geology is alluvial, or land use is grass and geology is shale, it is suitable. Otherwise, all the other cases except this one is unsuitable, right? So this is how the raster overlay operators can also be summarized. Okay, so you might be confused on what we have studied till now. So I've kept an overall summary of it at the end. If you look at vector overlay operators, we can do clip. So it extracts features from one layer using the boundary of another. Completely makes sense. We can use difference as well. Subtracts one layer from another, retaining only the areas that do not overlap. Intersection retains only the areas where both the layers overlap. And union means combines two layers, keeping all features from both. So there will be, in the attribute table, both of those attributes would be combined, right? And if you look at raster overlay operators, there'll be arithmetic operators like addition, subtraction, multiplication, and division, and where we look at NDVI as well, where there was combination of plus, minus, division, and everything. There'll be logical operators where it'll be and, or, not, and as well as we will have XOR. XOR. And there will be comparison operators greater than, less than, etc., etc. And there will be conditional expressions operators as well, if then, right? So if this is there, then this is true, and if this is not there, then this is false, or something like that. So what do you need to understand in this section? We are just studying about vector overlay operators and the raster overlay operators, and I think this is all that you need to understand the basics of these operators. Of course, there are multiple operators more than this, but these are the basics on which you first will dive into when you are going into any basic or introductory GIS things. Okay, so thank you so much for listening. Bye bye.